Now we shift gears and we talk about the other very important type of bonding that we'll be examining in Chemistry 139, and that is the covalent bond. So, in the early 20th century, there was an American chemist by the name of Gilbert N. Lewis, and he devised a pretty simple model for describing the bonding in chemical compounds. First thing that he noticed is that valence electrons, those that are in the outermost shell of a representative element, they're the ones that are most important in bonding and the ones that are going to interact when atoms come together. G. N. Lewis, he said that valence electrons are transferred between elements that are very different. So between metals and non-metals, we see the transfer of electrons when those atoms interact, and this results in the formation of ionic bonds. However, when we have similar non-metal elements, when those atoms come together, electrons are shared and we form what are referred to as covalent bonds. Now, whether atoms either share or transfer electrons, the net result is that the atoms will continue to share or transfer electrons until they obtain a stable, unreactive electron configuration, which we describe as being a complete octet. That is, they're going to either share or transfer electrons until they obtain a stable noble gas electron configuration. I should point out that there is one exception to atoms becoming stable when they obtain 8 electrons, and that's hydrogen, which has an electron configuration 1s1. Hydrogen loves to obtain the electron configuration of helium, which is 1s2. And so hydrogen doesn't need a complete octet to have a noble gas configuration. Hydrogen has a complete octet when it has 2 electrons. So we should recognize that atoms form covalent bonds with each other by sharing electrons. So there are some atoms, when they come together, they get stuck. They stick to one another, and hydrogen is an example of that. We don't ever find individual hydrogen atoms in nature. We only ever find hydrogen present as 2 hydrogen atoms stuck together. So it's interesting to think as to why that might be. So let's consider 2 hydrogen atoms that are separated by a very large distance so that they can't possibly interact with one another. And each hydrogen atom will have a nucleus that has just 1 proton in it, and then about that nucleus there is 1 electron orbiting. So these atoms are so far apart that they can't possibly interact with one another. Now what we're going to do is we're going to bring these 2 atoms together, or we can imagine these 2 atoms colliding to one another and observe what happens. So the atoms are going to come together so that the regions of space where their electrons are found now overlap. And what we find is that we form a very stable arrangement of particles where the 2 atoms become stuck to one another. So if I think about all of the forces that are going on here, there's going to be electrons interacting with electrons, and that will be repulsive. And the protons on each of the hydrogen atoms will also be repelling each other. So these are all of the repulsive forces. But there will also be the inward attraction of one of the protons to 2 electrons, and there will also be the inward attraction of one of the protons to 2 electrons. This is going to be the case when the electrons sit or are shared between the 2 atoms. And it turns out that when we think about the distances here, this proton interacting with this proton, there's quite a large distance there, so that's really weak. Okay, so that doesn't really do much. And so these attractive forces over here win out, and these atoms get stuck together because we have a positive interacting with a double negative in each case. Okay, and that's a very strong attraction and can easily counter the little bit of a repulsion that we get from having the two electrons being near one another. Now it turns out that there's like sort of like a sweet sort of distance between these two nuclei that maximizes the attractions. If they get too close, these guys do start repelling one another, and that becomes a bit of a problem. But when they come together, they collide. If their electrons sit in between the two nuclei, exactly halfway in there, each nuclei will feel an inwards attraction towards those two electrons, and that'll hold the two atoms together, forming an H2 molecule. So a covalent bond is the attraction that two nuclei will feel towards a pair of shared electrons. That's literally what a covalent bond is. So, in ionic compounds, things are sort of a little different from in molecular or covalent compounds. Ionic compounds contain dissimilar elements. Most of the time, this is a metal with a nonmetal. And what holds them together is the attraction between oppositely charged cations and anions. Ionic compounds exist as crystals. There are no molecules in an ionic compound. The crystals are approximately infinite. Ionic compounds have really high melting points, and they are all solids at room temperature. Now, molecular compounds are formed between non-metals that are all bunched over on the right of the periodic table. Sometimes they're even formed between the same non-metal atoms as we saw with the hydrogen molecule. What's holding together a molecular or a covalent compound is the attraction for the nuclei of the atoms to shared electrons. That's what's holding them together. Now, molecular compounds don't consist of an infinite array of atoms bound to one another in all directions. They consist of discrete molecules. So we might have a hydrogen molecule over here, and a hydrogen molecule over here, and a hydrogen molecule over here. And these hydrogen molecules can be moving around, doing their own thing, barely interacting with each other. That's very different from in an ionic compound where, one particle is in a network of connections with a bunch of other particles, which is in a network of connections with a bunch of other particles. So they tend to be very solid sort of structures. For molecular compounds, we will often find some are solids, some are liquids, some are gases, because these molecules are really just moving around, doing their own thing. It's a very different scenario from what we see for ionic compounds. So bonding can be characterized as either being ionic or covalent. Covalent bonding, though, occurs between non-metal atoms, and it arises as a result of sharing of electrons. Why do the atoms share electrons? They do that in order to obtain a complete octet, just like atoms will transfer electrons also to obtain a complete octet. What holds the atoms in a covalent compound together is the attraction between the nuclei and shared electrons that sit between the nuclei of different atoms. Covalent compounds have molecules as their building blocks. They're not crystalline materials where there is a network of connections between atoms. There's just a few connections between a few atoms. Molecular compounds are not all solids at room temperature like ionic compounds. They can be solids, liquids, or gases. They're kind of a little bit all over the place. A good example of a solid covalent compound would be iodine, but something like oxygen is a gas. Water is obviously well-known liquid at room temperature. So, we previously saw that we could use Lewis symbols to indicate how electrons were transferred from metals to non-metals to form ionic compounds. The question now becomes, can we do the same for molecular compounds, is there a way of using Lewis symbols, named after G.N. Lewis, to indicate how electrons are shared in molecular compounds? And of course the answer is yes. So let me give you a few examples of how we can illustrate the sharing of electrons. So think about what might happen when a hydrogen atom, which is in group 1A and has one unpaired dot in its Lewis symbol, comes into contact with a fluorine atom, which is in group 7A and also has one unpaired dot in its Lewis structure. You want to think of these unpaired dots as like a hand reaching out, looking to grab onto another one and kind of have a handshake. That's how you want to think about these guys. So these guys come together and they share their unpaired dots. What you suddenly realize is that hydrogen now has 2 electrons around it, so it's become isoelectronic with helium, and fluorine now has 8 electrons around it and has become isoelectronic with neon. So they're all very happy because they both have a noble gas electron configuration. It gets a little bit confusing because we've got a lot of dots around this fluorine atom here. So what we will do is we're going to kind of use a symbolism that shows that when electrons are shared and when they're not being shared. When electrons are being shared, we draw them as a line. And when they're not being shared, we draw them as dots. So those 6 dots that are around the fluorine belong exclusively to the fluorine. They're not being shared with the hydrogen, but the single line in there is indicating that that is 2 electrons being shared. So one line is equivalent to 2 electrons being shared. So when 2 fluorine atoms come together, fluorine is in 7A, group 7A of the periodic table. They each have one unpaired dot in their Lewis symbol there. So these guys are going to grab onto one another because that's what they kind of do. And then now you can see they're going to get stuck, and each of them will have a share of 8 electrons around them. 2, 4, 6, 8. 2, 4, 6, 8. Perfect. It's these 2 electrons in the middle here that are being shared, so we're going to indicate that by replacing those guys with a single line. And so these are what examples of what we call diatomic molecules. Now molecules can be bigger. They only involve 2 atoms. They can be bigger. They can be heteroatomic molecules, or they can be homoatomic molecules, right? Okay. So kind of reviewing what we had before. So electrons within a molecule are classified either as bonding electrons. These are the ones that are being shared, and we mentioned that for every pair of electrons that's being shared, we'll often replace that with a single line to make it clear. And then there are these other electrons that belong exclusively to one atom. They're not actually helping the molecule hold together, and they're referred to as non-bonding electrons. And because they come in pairs, they're often referred to as lone pairs. So those guys don't actually help the atoms stick together. They belong exclusively to one atom and are not shared. Now, we can go more than diatomic molecules. We can go to triatomic molecules or tetraatomic molecules, and even bigger. Sometimes we go up to molecules where there's like dozens of atoms in them. So here's an example where we have 2 hydrogen atoms combining with an oxygen atom to make water. And what we see here is oxygen's in group 6A. It's got 2 unpaired dots. Each of the hydrogens has 1 unpaired dot because they're in group 1A. By sharing these guys like this, the oxygen gets a complete octet and it becomes like neon, and then the hydrogen ends up with its 2 electrons which it loves, and it becomes like helium. So when we look at this, when we replace the pairs that are being shared, with the lines, we end up with a familiar, well, it will become very familiar to you. We end up with the Lewis diagram of water, where we have two bonds here to the oxygen coming from the hydrogens, and then you can see that the oxygen has two lone pairs that complete the octet. So we can go 2, 4, 6, 8, and feel happy that this is a good Lewis structure because the oxygen has a complete octet. Here we have nitrogen. Nitrogen has 3 octet vacancies, or 3 unpaired electrons. It loves to make 3 bonds, and so it will readily pair up with 3 hydrogen atoms, and then the nitrogen atom, you can see 2, 4, 6, 8, has 8 electrons around it, has a stable octet, and every hydrogen atom has a share of 2 around it, so it has a helium configuration. Replacing the shared pairs with the lines gives this diagram here, which kind of makes everything very clear. The nitrogen has 1 lone pair in this case, and then forms 3 bonds, each comprising 2 bonding electrons to the hydrogens. Now when we go out to carbon, carbon's in group 4A. It has 4 unpaired dots around it, loves to form 4 bonds, and we can go through the same process. Carbon doesn't have any lone pairs on it in this compound here, which is called methane. So the number of unpaired dots in a non-metal's atom's Lewis symbol indicates what we call the number of octet vacancies, and this is the number of bonds that it commonly forms. Now, it doesn't always form that number of bonds. We'll see later on that there is a compound called carbon monoxide, and in carbon monoxide, carbon is forming only 3 bonds, even though carbon loves to form 4 bonds, and oxygen is forming 3 bonds, even though oxygen loves to form 2 bonds. It's just what the atom tends to form. Sometimes it doesn't kind of run with the program. So Lewis structures can be drawn to show how electrons are shared in covalent molecules. When forming a covalent molecule, an atom will tend to form the same number of bonds as the number of octet vacancies or unpaired electrons in its Lewis symbol. That's how it's going to complete its octet. Remember that the number of dots that a non-metal atom has around it is just equal to its group number. So there's carbon in group 4A. It's going to have 4 octet vacancies, 4 valence electrons. If I go to nitrogen, or let's actually go out to fluorine, which is in group 7A. Fluorine is going to have 1, 2, 3, 4, 5, 6, 7 valence electrons. So it only has the 1 octet vacancy.